Okay, welcome back. Still chapter 6, so let's get started. The first question is dealing with the de Broglie equation. So let's remind ourselves of that. It is the wavelength. And remember that de Broglie is concerned with the wavelengths of matter. So the wavelength equals h over mv, where m is mass, v is velocity. Let's also remember, too, that 1 joule equals 1 kilogram meters squared per second squared. Okay. Alright, so this is just really conversion problems. For the first one, we need to take all the units into these standard units so we can get joules. So, we have 30 kilometers per hour. We're going to take that to meters per second. So there are 1,000 meters in a kilometer. So our units cancel. And then there are 60 minutes in 1 hour. Our units cancel. There are 60 seconds in 1 minute. Our units cancel. So now we are in meters per second. So plug it into the calculator. That is 8.3 meters per second. Okay, now I'll plug into the formula. Wavelength equals h, so 6.626, our constant, our Planck's constant, divided by the mass, 105 kilograms, times the velocity, 8.3 meters per second. Units will cancel to give us a wavelength. So doing that out in our calculator, we get 7.6 times 10 to the negative 37th meters. Extremely small wavelength. Moving on, 8-gram bullet is fired at 400 meters per second. So again, 8.0 grams. We know there are 10 to the third grams in 1 kilogram. So we get 0.008 kilograms. Okay. Now we plug in again. So again we have our formula. Our speed is already set. And we will get 2.1 times 10 to the negative 34th meters. So again, a very small wavelength. Okay, the third one is a sodium atom. So this one's going to be a little bit different. We need to look up the molecular weight of sodium from the periodic table. So it is 23. Well, let's use the exact number. 22.99. Okay, so we need the mass of a single atom. So let's start with the molecular weight, 22.99 grams per mole. Alright, so again, there's 10 to the third grams per kilogram. Alright, so now we need to use Avogadro's number to figure out how many atoms per mole. So 6.022 times 10 to the 23rd sodium atoms in 1 mole. Okay, so now moles cancel. Okay, so we plug all that in. And we get a very small number, which is what we expect. 3.8 times 10 to the negative 26 kilograms. So luckily our speed's already converted. So now we plug in again. We have H. That's Planck's constant. We divide by our mass. Um, 3.5 times 10 to the 6th. And our answer will be again in meters. Because we are using standard units for everything else, we can be reasonably assured that our answer will also have standard units. So that's a good thing. So we get 4.9 times 10 to the negative 15th meters. Okay. And lastly, an ozone molecule in the atmosphere. So again, ozone, the molecular weight is 48 grams per mole. So again, converting 10 to the third grams per kilogram. Okay. 1 mole has 6.022 times 10 to the 23rd molecules. Okay. So everything's going to cancel out nicely for us. So we carry out the operations. And we get, again, a very small number. So it is going to be 7.9 times 10 to the negative 26th kilograms. And again, we plug into the de Broglie equation one more time. That's 7.9 times 10 to the negative 21st kilograms times our speed, which is 650 meters per second. So plugging all that back in. Doing all the math. We will get 1.3 times 10 to the negative 16th meters. So this is basically an overview on how to use the de Broglie equation to find wavelengths of matter. You plug in what you know, and you use this top equation to calculate. Thanks for watching.